Hello everyone, and welcome to the last lecture of Computational Algebraic Geometry. So today I want to talk about periods of hypersurfaces. This is a generalization of the periods for curves. So the subject gets a little bit more technical, but I would like to give you a quick tour so that you at least know that it is possible to compute periods of hypersurfaces and you have a portion of the tools necessary to do so. So we begin by taking a smooth hypersurface again. T will be the degree of x, and x is cut out by a single polynomial f. Okay, so we talked about the Hodge decomposition of the cohomology. So I wrote this as a sum of spaces indexed by pq like this. And today we will learn a little bit more about this decomposition. Let me remind you that I'm talking about the Hodge decomposition. And when we talk about periods, really what we talk about is this decomposition. So let me say it in this informal way first, so that the periods of x record the Hodge decomposition, or the pieces of these subspaces inside of the cohomology. And you would like to record this decomposition with respect to the integral structure. Otherwise, the only invariant, if these were just abstract complex vector spaces, the only invariant of this vector space decomposition will be the dimensions. What makes periods interesting is that there's also this integral structure. So there's a lattice inside, and we want to record this Hodge decomposition with respect to the integral structure. So if you want to get all philosophical about it, the decomposition is complex analytic in nature. In fact, it turns out that it's purely algebraic. You can even define it even if we weren't working over complex fields. So this side is algebraic. On the other hand, the integral structure is topological in nature. So that when you try to combine the two sides, which is what periods do, then you're combining the algebra and the topology. And this is kind of delicate, and you can have this sort of thing most clearly over the complex numbers. So that's why it's kind of valuable and very interesting. But I will also state a theorem that tells you how precious these periods really are. So this is usually called the Torelli theorem for hypersurfaces. So the reason we talk about Torelli is that we saw the Torelli theorem for curves, and this is a generalization of this theorem. The proof actually is due to Donagi from 1983, and strengthening of this result, which is the one I'll be quoting, is due to Voisin. So this is from 2021. This is 1983, 2021. Well, and the statement, just like the original Torelli theorem, is going to say that if you know the periods, that is, if you know the Hodge decomposition, then you can recover x. Except there are a few caveats. So first of all, we have to say that except for finite many n and d, so except for finite many dimensions and degrees, and we have to say for a very general hypersurface. So I'll have to explain what very general is in just a minute. So this whole hypersurface is of degree d and in Pn plus 1. The Hodge decomposition, or more formally this Hodge structure, or for us it will be periods, and together with the integral structure with its intersection product I won't mention here. So this Hodge decomposition is enough to recover the hypersurface. Of course, up to isomorphisms. So you cannot recover the equation, that's too much and it's a little bit silly, but you can recover the hypersurface as an abstract object. So one thing I hid here in the word Hodge decomposition and periods is that there is an intersection product here, and this is called polarization. I'm ignoring this thing because it's a discrete invariant, so it doesn't deform with x, for example, it stays fixed. So we can just ignore this issue. What's delicate here are the periods. So essentially those periods determines the hypersurface, or to look at it in another way, there's a transcendental way of defining x. Well, if you want to read the latest version and the proper statement, you can look at Voisin's paper, which I'll be citing below. She also gives the full list of exceptions. Let me just give the few low-dimensional exceptions, just to show you that, in fact, there aren't many exceptions. So n equals 1, which means for curves, we know there are no exceptions. So this is Torelli theorem. I should warn you that Voisin assumes a less structure than I've assumed here. She ignores the polarization, she ignores the integral structure, so her statement is a stronger statement, but then a few exceptions arise. For example, genus 3 curves become an exception for her. But with the way I've stated it, all curves can be recovered. This is Torelli theorem. N equals 2, the only exception is when d equals 3. So only cubic surfaces are an exception. And the reason is that for cubic surfaces, this 1 part of a cubic surface equals the whole cohomology. So we know how to compute the Hodge numbers. You can compute the Hodge numbers for a cubic surface, and you'll see that this is indeed true, which means there is no variation in Hodge structure. There's nothing here. All cubic surfaces have the same Hodge structure, but not all cubic surfaces are isomorphic. That's the only exception here. Now, when n equals 3, so we're looking at threefolds in P4, the only possible exception was d equals 5. I'm saying the only possible exception in the sense that there's a list of possible exceptions, d equals 5 is in that list, but an older paper of Voisin handles this case so that there are no exceptions here. So quintics are Calabi-Yau's and they're also very special, so that was one reason of interest. I believe Voisin's paper for this is 2010. And then for higher dimensions, there are two infinite sequences of possible exceptions. I will not write these infinite sequences here. You can check Voisin's paper or Donagi's paper. The point is, these infinite sequences were first given by Donagi, and what Voisin does is that she proves that at some point we can truncate these infinite sequences and we'll ignore the infinite tail. Finitely many of these already contain all possible exceptions. So she doesn't give an explicit cutoff point, so that would be very interesting to find out. It should be possible to give an explicit finite list containing all possible exceptions. Not everything in the list is necessarily an exception, but at least we can find perhaps an explicit cutoff point. Okay, so what I'm going to do today is that I will explain to you an algebraic way to represent this Hodge decomposition. So this is a very important tool. It's like a textbook level tool that appears in Donagi's work. It's now in Voisin's textbook. So it's very important, and it will give you an idea of how one might compute the Hodge decomposition in principle. So the way I'm going to describe the Hodge decomposition will also be helpful in realizing how to compute it, but I can only get you about halfway there. So I will tell you how to compute the forms, but I cannot tell you how to compute the topological cycles. Anyway, so we need two simplifications to continue. One of them is we need to change our description from this decomposition to filtration. This is just a notational change in principle, but it's a very useful, a more natural construction is the filtration. And after this, I need to introduce the primitive cohomology, which is just the usual cohomology. So it's this cohomology again, especially when n is odd, then the primitive cohomology is the usual cohomology. Except when n is even, we have to throw out one thing from this. Maybe you'll remember that when we were computing the Hodge decomposition, we had a Dirac delta when p equals q. That's something we subtracted. Well, now we're going to subtract that thing really from this space. So that's the more natural object. So in principle, you can skip the rest. It's mostly about notation, but I have to introduce it. Okay, so here's the filtration. So for every r, we define the following space. It's the fr of hn. And the way you define this is that it's going to be sum of the pieces, these Hodge pieces, where p is greater than or equal to r. So if we were to write it, so the maximum that p can attain here is n, and then q is 0, and that I'm not writing the x's anymore. And then you have n minus 1, 1, and so on. So you'll get to h, r, n minus r. So in particular, Fn gives you just this piece, Hn0. F0 gives you everything, the entire cohomology. So usually write the filtration like this. So you have Fn, Hn as the smallest piece, and I'm not now writing the C anymore. In other words, the filtration, instead of giving subspaces like the Hodge decomposition, it gives you a nested sequence of subspaces. So it has this additional structure. As I said, this seems just like a simple manipulation of you can go from one to the other. So there is an additional structure such that these spaces are orthogonal to one another. HPQs are orthogonal to each other. So there is this additional structure, this intersection product, that allows you to recover HPQs once you know the filtration. But the reason you want to work with the filtration is that it turns out that this is the more natural object. For example, if you were to vary the equation of x, then these things vary like fibers of a holomorphic vector bundle. Whereas these things absolutely do not, because they have relations that mean HPQ is complex conjugate of HQP. So if HPQ were to vary holomorphically, then HQP would vary anti-holomorphically. So that this thing certainly cannot live, so its variation cannot live in our category of complex analytic objects. This thing does. And whenever your object survives variation, it usually means it's the more natural object. And there's one more reason why this is the more natural thing. So this thing, which is called the Hodge filtration, once again introduces an element of what's called the flag variety. So a flag variety is a generalization of a Grassmannian. So what was a Grassmannian? A Grassmannian, you said, you gave me one dimension and the ambient space, and it parametrized all subspaces of that dimension. A flag variety takes an increasing sequence of dimensions and it parametrizes all subspaces of those appropriate dimensions. So this lives in a product of Grassmannians. Remember that up to change of coordinates, the only invariant here would be the dimensions, and that would be kind of stupid. So here we say that the only change of coordinates you're allowed are the ones that preserve the integral structure. So the GL of this lattice is allowed to act here. That makes this point presenting the Hodge filtration a valuable data. In fact, this filtration is equivalent essentially to the periods. Okay, so that was the first of the two notational corrections that we had to do. So we went from decomposition, the Hodge decomposition to Hodge filtration. Now I need to tell you about this primitive cohomology. So at its heart, primitive cohomology just means the cohomology classes that don't come from Pn, from the ambient space Pn plus 1. But if we were to be a little bit more formal, you can say this. So you take lambda to be a hyperplane, so a degree 1 hypersurface. So this would be the zero locus of, for example, x0, one of our coordinates. Doesn't matter which one you take. And then you intersect this with x. So when you intersect it and you take the homology class, x is of dimension 2n. This is a complex hyperplane. It cuts down the complex dimension by 1, real dimension by 2. So it gives me a homology class here. This homology class is independent of the equation and is usually called H. So this homology is isomorphic. This is by Poincare duality to H2. So it gives me a cohomology class. And then I have powers of this thing. So if I were to take the kth power, which is the same thing as taking a codimension k linear space and intersecting with x. I will not write this here. You can think of it as using the cup product on cohomology. This thing will live in H2k for any k. Now these are the classes that sort of come from the ambient space, and we are interested in things that do not come from there. And the definition we're going to use is that the primitive cohomology, denoted by a 0 here, sometimes by writing prim here, is the following. It's either the original cohomology group, and then we don't have to worry about anything. N is odd. But if n is even, what you do is you take this power of h, so then of course this thing lives in Hn, and then using the intersection product Hn with itself, you take the orthogonal elements. So all elements in Hn that are orthogonal to this element, if n is even. So this is a non-zero element. If you take the orthogonal things to it, you cut down the dimension by 1. So the dimension of Hn of x C0 is either dimension here, which we call Bn of x, the Betti number, or Bn of x minus 1. And you know what's not orthogonal to hn over 2? hn over 2 itself. So when you intersect hn over 2 with itself, you get the degree of x. In particular, it's not orthogonal to itself. That's the extra element comes from Pn plus 1 that we're removing from cohomology. And in the previous lecture, when we were writing down the generating series for the Hodge numbers, we removed the contribution of this element, or rather the contribution of dimension 1 of this element, by subtracting this Dirac delta from our generating series. So let us also combine these two objects, the filtration and the primitive cohomology. Very briefly, we say that the filtration on hn of x c0, so on the primitive cohomology, is simply the filtration on the original cohomology group, except you intersect it with the subspace that you want to bring it down to. So you put your favorite number here, r, and this is the filtration on primitive cohomology. Okay, so now let's define the period matrix for a hypersurface. We've defined the period matrix for a curve, and this will be a generalization of it, but we need to be more deliberate about the structure that we sort of secretly hinted at with the curves. So now we take a basis for hn 0. So let's say m prime. So the dimension of this primitive cohomology is m prime. Prime is m or m minus 1, and m is the dimension, the middle cohomology. So this thing is a basis. So here omega is a basis, and if we can use a subsequence of this basis to generate the filtration, we say this thing respects the filtration, and in particular it gives us the filtration back. So so if there exists a sequence, say in minus 1, and so on up to I0, such that the smallest piece, I'm not writing x or c anymore, this thing is generated by omega 1 through omega in, and then of course this thing is inside fn minus 1 hn. This thing is generated by omega 1 up to omega in minus 1, and so on. So this I0 obviously has to be m prime. Right, so I've structured my basis so that subsets of my basis and nested sequence of my subbases form a basis for this filtration. So if this is the case, then the basis omega I is set to respect the Hodge filtration. Okay, so this was the first ingredient. Now I need the information for the integral structure. So this gives me information about the filtration. The other piece comes by choosing a basis for the integral homology. And now you combine the two. So you say the period matrix is the integral of these omega i's against this basis for homology. So here, of course, I'm calling it the period matrix, but it's well defined only after you've chosen all these bases. Once again, the rows are the coordinates of the omega i's, and the columns correspond to the homology cycles. And when I talk about you giving me a period matrix, it's understood that I also know the numbers. So I know the dimensions of the Hodge filtration, which is determined by the degree and dimension of x anyway, and the intersection product. So this matrix of the intersections of gamma and gamma j. So this is not quite determined by n and d, but almost. So this thing actually is a piece of information that you need to tell me. But anyway, so I assume this is always given to me together with a period matrix. And then this information, the period matrix and this data, is what you can consider as the input to the Torelli theorem for hypersurfaces. So that determines this Hodge structure. So let me make a remark here. So because the Hodge structure has the following property, that PQ is complex conjugate to HQP, we can omit the lower half of PX. In fact, a little bit more. We can omit a half of the PX, and in fact a little over half, as I will show you. And from that half, we can recover the Hodge structure. So why is this useful? I will show you with it, but we've seen this already with curves. That I did not work with a 2G by 2G matrix, but I worked with a G by 2G matrix. I only recorded the position of H10. And another note, it's possible to complete the period matrix, which I've given you for the primitive cohomology against homology. You can complete it to the usual cohomology against the usual homology by adding one extra vector. So the thing you're supposed to add is that fn over 2. I will not get into this. Okay, so let's do a few examples. So to illustrate this 1/2 concept. So here f1, which is just the holomorphic forms on the curve, is enough to recover the Hodge decomposition. So you take exactly 1/2 of px. For n equals 2, this observation is a little bit more useful because it turns out that f2, which are now the global holomorphic 2 forms on x, on the surface x, is enough. So not only am I ignoring h02, which is its complex conjugate, but I can recover h11, which is orthogonal to h20 plus h02. And of course that's typically a huge reduction in dimension, so you can throw a large portion of px. And just to show you that the situation is different afterwards, here you need f3 and f2. So these are global holomorphic 3 forms, but this is something else. This is enough. So here once again you use exactly half. You don't use f1 and you don't, well, use f0, that's everything. So you don't need to complete this half to end basis for the cohomology. To further give an example to this n equals 2 case, if you take n equals 2 and d equals 4, so this is the first time when f2 is not empty, for d less than or equal to 3, f2 is empty. The dimension of h20, which we remember is denoted by little h20, this is 1, which means we only need the first row of px. So this is in fact a K3 surface. This first row is an element, well, it's a row vector of size 22. This first row is called the period vector of a K3 surface. And here we have a stronger Torelli theorem. So that in fact any K3 is determined by its period vector. So that this hedging your bets about being very general can be ignored. Okay, so this gets us to the portion where we've defined enough to revisit the theorem. So we have this Torelli theorem. I basically told you a way of representing the periods. So this period matrix, and that in principle is enough to recover the surface, or at least this isomorphism class. So what I skipped was this notion of being very general. Now let me say a few words about this part. So a naive interpretation here is useful. What the statement would imply is that if you were to randomly take f with coefficients random complex numbers, then with probability 1, you'd satisfy this condition of being determined by your periods. But there's a very specific definition for being very general, and it's this. See, f has a bunch of coefficients that determine the polynomial itself. These coefficients live in a affine space or projective space. Scaling it won't influence x. So in this affine or projective space, there are countably many, possibly infinite, but only countably infinite, subvarieties, where if f lives outside of this collection of subvarieties, or its coefficients don't lie in these subvarieties, then this condition is satisfied. So a very general typically means in the complement of countably many proper subvarieties in some parameter space. So the parameter space here is the space of polynomials. And I just showed you that if you take n equals 2 and d equals 4, you can just work with a period vector, and it turns out that in that case you can omit this very general case. It's true for quartic surfaces. Now what I want to talk about is a little bit more about how to represent this matrix. So this period matrix is an integral of forms against homology cycles. I want to tell you how to represent the forms explicitly. Remember, we did this for curves. I was able to write down an explicit basis for cohomology, or rather for holomorphic forms. And so what we're going to do is to write an explicit basis for cohomology that respects the Hodge filtration. And let me tell you what is not going to be in the second part. What will not be will be how to compute the integrals. So for curves, there was an explicit way to represent the loops generating a basis for the first homology. So it turns out that the first homology is particularly simple to handle, so it was possible to do this almost manually. In general, it's very hard. So I have an implicit method to compute or to represent these bases so that you're able to compute the value of these integrals without actually computing an integral. And I will cite this also in the info box, but this takes us too far afield, so I will not do this. The trick here is only to deform x to a simpler hypersurface with a lot of symmetries, and where you can represent these gamma j's manually. Then you have to understand when you deform x back, how do these integrals change. So this is a story for some other time perhaps. Okay, so the second part of this lecture will be about this part, and then we will end this lecture series.